Good morning, everyone. Myself, Dr. Amit Shrivastava, and I'm professor in CSE department, SIRT, Bhopal. So today we'll be starting our lecture 5 of module 2. In this lecture, we will cover segmentation with paging, buddy system, and some numericals. So what is segmentation? Actually, segmentation supports the user point of view. Like as a user, when I make a program, then what do I think of a program? I don't think about a program in terms of paging. Rather than I think about a program by combining different functions, different modules, like that. Like suppose I have got a program which is consisting of main program, procedure, functions, methods, object, local variables, global variables, stack, and so on. So I'm thinking in terms of these modules. So operating system says that why to make paging concept, rather than we can go for the user point of view, that is in terms of modules. So here what we do, we subdivide our program into different segments or different modules, and these segments are loaded as it is in the main memory. So since these segments are of different size, so obviously we will require different memory for different segments. So again, it will be having both external as well as the internal fragmentation, as we have already seen in our previous lectures. But the benefit is that when I upload or when I load the complete program, then the contiguous memory requirement is much more than when we load these segments, because these segments are, let us say in this example, we are having 5 segments. So it simply means that I will be requiring, the memory requirement will be only 1/5 of the total program, right? So rest, everything is same. The only thing is contiguous memory allocation requirement will be less in case of segmentation, rather than when we upload or when we load the complete program. So here we have got 4 segments, and I have loaded these 4 segments in the memory, physical memory space. So all of these segments are requiring different memory space. So in this case, the CPU will be generating the logical address in the form of segment number and the offset within that segment. Since each segment is of different length, so we have to keep 2 fields in our segment table. One is the limit, that is the length of that particular segment, and then the base address of that segment. So this segment is first of all searched into this segment table. Here we will compare the limit or length of this segment with the offset, because this offset is within the segment. So this offset should be less than the length of the segment. So we check it whether D is less than this limit. If it is not less than, then we will simply trap it, and it is an error, we will terminate the program. In case it is yes, the offset is less than the length, then we will simply add the base address of the segment to this offset to get the physical address. So this is how we will be translating the logical physical address in case of segmentation. So we have got one register also, segment table based register, which points to the segment table's location in the memory. Another register is STLR, that is segment table length register, which indicates the number of segments used by a program. Okay. So let us look at this example. Here I've got 5 segments, and these 5 segments are having the lengths and the base address of these segments as shown in the segment table. Now we have to convert the logical addresses into the physical address. So suppose I have got logical address of 2, 500. 2 is the segment number and 500 is the offset within that segment number. So first of all, I will be going to the segment table and check whether this segment 2 has got the length greater than or equal to this offset or not. So here we see that segment number 2 is having the length of 400, and we are trying to access 500th address within this segment. So it is an invalid address. Okay, next we have got segment 4 and 700 is the offset. So in this case, we have got segment 4. So we'll check segment 4. Here the length is 1000 and the offset which we are trying to access is 700. So this 700 is less than 1000. So it is a valid address. What we will be doing, segment 4 base address, that is 4700, we add this to the offset to get the physical address. Similarly, segment 0, 995. So segment 0 has got a length 1000 and offset is 995. It is valid. So the base is 1400. So 1400 plus offset, that is 995, gives us the physical address. So this is how we are going to convert the logical to physical address in case of segmentation. Now another concept is segmentation with paging. So now since we are when we are using segmentation, then we have got the problem of external as well as internal fragmentation both, and also the segment length is much higher than the page. So for segmentation also we have we have to find less memory contiguously as compared to the complete process, but still it will be the contiguous memory requirement in case of segmentation will be much higher than the paging. So why don't we combine this segmentation with paging? So this is the concept which we use, segmentation with paging. So what we do, we first of all create different segments, then these segments are further subdivided into pages which are fixed size pages, and whatever is the size of the page in the logical address, then the same fixed size blocks are maintained in the main memory also, which we are calling frames, as we already know. So first of all, in this case, what we have to do, we first of all find the segment number in the segment table. From this segment table, we will be getting the address of the particular page table, which is maintained for this particular segment. It means that if I've got 5 segments, then I will be maintaining 5 page tables for this process. Okay, each segment will have different page table. So from here, I will get the base address of the page table for this particular segment. From there, I will be going to that page table. Here, I will be searching the page number within that segment. Then, from this page table, I will be getting the frame number. This frame number will then be added to the offset to get the actual physical address. So this is how we are going to translate the logical address into the physical address. So here the logical address will be consisting of 3 bits: segment number, then page number within that segment number, and then the offset within that page number. All right. So next we will be seeing the buddy system. So in buddy system, we allocate the memory in the power of 2. Okay. So for example, if we want the process 50K is the size of that process, and we want to allocate memory, then we will allocate the memory in terms of power of 2. So 64K of memory had to be allocated to 50K, right? Because if this is 2 to the power 5, it is 2 to the power 6, because less than this 2 to the power 5 will be giving us 32K of memory, and 32K of memory will not be sufficient for holding the 50K process. So we have to go for higher side. So the 64K of higher than 32K, the next will be 64K. So this will be allocated to this 50K process. So let us take an example. We have got 1 MB of free space available to us. A request come for 100K. So we'll subdivide this 1 M into 512 and 512. Again, this 512 will be subdivided into 256 and 256. Then this 256 is again subdivided into 128, 128. And then this 128K will be allocated to this 100K. Yes, there will be lot of internal fragmentation in this concept, but memory allocation and deallocation will be very, very easy as we are working in terms of 2. Fine. So the speed of execution of this particular kind of system will be very fast, as the calculations will be very fast. But the memory requirement will be much higher as compared to the previous systems which we were using. Okay. Next, the request come for 240K. So we have to allocate 256K. So we have allocated here. Then the request for 64K. So we can subdivide this 128K into 264K. We can allocate here. Then next again 256K. So we have to go for the next block here. So we'll give 256K here. Then we are releasing B. So we will be releasing this 256K. So the memory is freed up and so on. So we can see here the allocation and deallocation is done in terms of the memory, which is of the power of 2, and it is very fast in case of buddy system. Fine. So let us consider now some numericals. A program containing relocatable code was created, assuming it would be loaded at address 0. In its code, the program refers to the following addresses: 50, 78, 150, 152, and 154. If the program is loaded into memory starting at location 250, how do these addresses have to be adjusted? So we will be making use of the relocation register, which will be loaded with the value 250, and all the addresses will be added this 250 to get the actual physical address. So if the logical address is 50, then simply add this 250 and we'll get the physical address of 300. If the logical address is 78, then simply add this 250 to 78 and we'll get 328, which is a physical address. Okay. Next question is, on a system with 2 to the power 24 bytes of memory and fixed partitions, all of size 65,536 bytes, what is the minimum number of bits needed in an entry in the process or page table to record the partition to which a process has been allocated? Okay. So here, what we have to do, we know that the partitions are of fixed size and their size is 65,536. So 65,536 is nothing but 2 to the power 16. Fine. So if we divide the number of bytes of total memory by the size of each partition, it will give us the total number of partitions which can be present in that particular memory. So we have got 2 to the power 24 bytes of total memory. The partition size is 2 to the power 16. So simply divide 2 to the power 24 divided by 2 to the power 16, it becomes 2 to the power 8. So it means maximum number of partitions which can be present in the memory are 2 to the power 8, and 2 to the power 8 is nothing but 64. So for accessing 64 different partitions, we will require 8 bits, right? So 8 bits will be required to store 2 to the power 8 partitions. Okay. On a system with 2 to the power 24 bytes of memory and fixed partitions, all of size 65,536 bytes, how many bits must the limit register have? The total amount of memory is irrelevant here, since 65,536 is 2 to the power 60. Therefore, the limit register must have 16 bits, because limit register will be accessing the offset within that particular partition. So we are only concerned with the partition size, not with the total memory. Okay, next numerical is, on a system using fixed partitions with sizes 2 to the power 60, 2 to the power 24, and 2 to the power 32. How many bits must the limit register must have? Since the system has only one limit register, so it must be large enough to accommodate addresses in any partition. So the largest partition is 2 to the power 32. Therefore, the limit register must be 32 bits long. So on a system using first fit allocation, assume memory is allocated as specified in the figure before. Additional requests for 20K, 10K, and 5K are received. At what starting addresses will each of these additional requests be allocated? So U is indicating utilized memory, H is indicating the whole. Okay. So we are using the first fit allocation scheme, means the first hole which we find, which is large enough to accommodate that particular request, we will simply be allocating that hole to this request. Okay. So let us see. We have got a new request of 20K, 10K, and 5K. Okay, so this is our memory location, and we want 20K to be accommodated. So first hole is of 10K, we cannot accommodate. The second hole is 30K, so we will allocate 20K to this hole. Okay. So out of 30K, we have allocated 20K to this process, and 10K again is left as a whole. Okay. Now we will simply combine this utilized memory together, and we will get this figure. Now the next request is of 10K. So if we see, the first hole is of 10K. So we will accommodate this 10K to the process. Then again, we will combine the utilized memory and so this is our next thing. And next request is of 5K. So 5K, the first hole is of 10K. So we can allocate here 5K itself. So we have allocated here. And then finally, this will be the memory structure which we will see. Okay, so that is all for this lecture. Thank you.